Welcome back to Knowledge is Power Educational Videos, the only place where you can get smarter by listening to dumb people. This is the engineering problem solving section. This is lecture 4, and today we're going to be discussing the fundamental dimension we brought up earlier, which is amount. We're going to be elaborating upon it and explaining it. So let's get started out here, and let's just talk about the reason that we have all the units we've gone over is to be able to keep track of the things that we measure, these quantifiable things that we want to measure. We have units to keep track of it. But a lot of the times, new units are invented simply to make things easier to express. For instance, if I told you the distance between two stars was, I believe, inaccurate is I think it's 620 quadrillion. Is it quadrillion? Yeah, it's quadrillion feet. Let's write that out just for fun. Let's see what we're talking about here. So that's going to be 620. Quadrillion is going to be let me see. We got hundreds, thousands, millions, billions, trillions, quadrillion. We got 620 quadrillion feet there. That's a lot. Wouldn't it be easier just to say that 1 light year is equal to 3.1 times 10 to the 16 feet? Therefore, this amount here is equal to 2 light years. That makes the whole process much easier than having to say that or to notate that or to write that out. The same thing applies, and now we're talking about things that are very, very large. Where amount comes in and why we have mole as the main unit for amount is when we talk about things that are very, very small. So instead of imagining these very large numbers and things, let's talk about things that are very, very small, such as molecules or atoms. The constant that we use was named after Amido Avogadro. Avogadro. I can never say his name right. I always say Avogadro. So just give me a break on that one. We're gonna roll with it. Anyways, that's an Italian scientist back in the late 1700s, early 1800s, who first proposed the idea that there's a fixed ratio between the amount of a substance and the number of its elementary particles. Okay, so he came up with the constant, and it's called Avogadro's constant or Avogadro's constant. Let's write it out. And we're going to come back to this number throughout. So we're just going to get it out here right now. 6.022 times 10 to the 23. And that's what we call a mole. And basically what it's saying is that there are this many, 6.002 times 10 to the 23 particles of something per mole. So if you imagine if we have 12 of something, we have a dozen, right? If we have 20 of something, we call that a score. If we have 6.022 times 10 to the 23 of anything, we can call it a mole. Okay? Now, we're not going to use this to say, like, oh, we have a mole of elephants or anything crazy like that, because those are large things. We're talking about very, very small things when we use moles. And we're talking about, particles, atoms, and things of that nature. So, let's talk about how we came to this constant. How did he come to this constant? Now, first off, the mass of a nucleon, neutron or proton, doesn't matter, is about, and scientists have come up with this, it's about this much right here. It's 1.66 times 10 to the negative 24 grams. Now, the same as up here where we came up with light years, to avoid having to use such tiny numerical values and write it all out and things like that, physicists came up with the term atomic mass unit. atomic mass unit. Also, this is an AMU is how it can be notated. It can also be, most people usually just notate it with just a U, which is normal. Also, I've seen it referred to as a Dalton, D-A, a Dalton. Now, let's imagine that there are, per 1 AMU, there are 1.66 times 10 to the negative 24 grams. Okay? Now, in order to illustrate this next step, I'm just gonna cut away, and you're gonna see we're gonna do this on the scientific calculator. So if we take this 1 and we divide it by 1.66 times 10 to the negative 24, you're gonna see we come out to approximately 6.022 times 10 to the 23 AMU/G. So let's write that out. 6.022 times 10 to the 23 AMU per gram. And this is the numeric value that defines a mole. Now, I just want to point out on the calculator that E is basically a times 10. It's scientific notation, Euler's number, such and such. But when it says E23 at the end there, that is saying times 10 to the 23, which is also Avogadro's constant, right? And this is the number that is used to define the mole. So 1 mole of any substance contains exactly 6.022 times 10 to the 23 of its fundamental units, its atoms or its molecules of that substance. So this is often written and notated as Na equals 6.022 times 10 to the 23 mole negative 1. As mentioned above, this is Avogadro's constant, and it's also oftentimes going to be symbolized by this Na. So why is this important? Why do we care about this, Randy? Let's consider you're a scientist and you're trying to combine hydrogen and oxygen to get water. You need twice as many atoms of hydrogen as oxygen for the reaction, because water is what? Water is H2O. We need 2 hydrogen per every oxygen. So, in other words, we need twice as many hydrogen as oxygen. We need 2 moles of hydrogen for every 1 mole of oxygen. And this is the thing. This is difficult to measure. Okay, this is difficult to measure. The problem is you can't really measure something directly in moles because it's such a tiny microscopic value. But the thing about Avogadro's constant is it gives us a link between the link, kind of like a conversion path between moles and mass. So here, let's do this. Let me pull up. Let me grab. We're going to pull some things off the periodic table here. So let's copy this image. We're going to come over here. Oh. All right, and let's paste this image. It's going to let me resize it. All right, it's not going to let me resize it. That's fine. And let's grab hydrogen off the periodic table. We're going to copy this image. Let's come over here. And we're going to... Why won't it let me resize that, I wonder? Paste this image. Seems like it would let you resize it. All right. And deselect. There we go. All right. So we're looking at now oxygen and hydrogen. Now, one of the things that we have to notice here is going to be, and these were right off the periodic table. One of the things we're going to notice here is going to be that, why do I still have this selected? All right. There. This number here, when you look at it on the periodic table, let me flip this. This number here, that's going to be the atomic mass units, the AMU, of each of these elements. I'll switch that back. So, if we're saying that we need to convert these to figure out how many grams per mole, or we're trying to figure out the mass that we need per the mole, we could say here, hydrogen's atomic weight is 1, right? Atomic mass. And so we're going to say that 1 AMU per a hydrogen atom. And we know that 1 gram is equal to 1.66 times 10 to the negative 24. And, oh, no, that's not right. That's backwards. This right here is also, we got to go ahead and define this as well. There is, oh, I'm getting ahead of myself. I'm sorry. Bring it back. 1 gram is equal to a mole. 6.022 times 10 to the 23 atomic mass units. Pretty much, right? And then we know that 6.022 times 10 to the 23 atoms is a mole. Let's bring this back. Now we need to figure out if we're trying to combine the right amount of oxygen and hydrogen atoms in order to create the perfect environment for there to be pairs of these exactly, we need to know what the mass of each of them needs to be when we go to combine them, right? So, we know from what we did up here that there are 6.022 times 10 to the 23 AMU per gram. So, let's start off. The atomic mass of hydrogen is 1. So we have 1 AMU per 1 hydrogen atom. Okay? Now the next step is going to be that we know that 1 gram, just from up here, is 6.022 times 10 to the 23 AMU. What else do we know? We know that there are 6.022 times 10 to the 23 atoms per 1 mole. And this leaves us with, let's do our canceling. We know that atom is going to cancel here. AMU is going to cancel here. So we are left with 1 gram per mole of hydrogen. So for a mole of hydrogen, it is 1 gram of mass. Let's do oxygen. Oxygen's atomic mass is 15.99. So we're going to say it's 16. AMU. And we know that's a oxygen atom. Now, all of this is going to be the same right through here, right? So we know what's going to happen. Everything's going to go, and we're going to be left with 16 grams per a mole of oxygen. So, with this, we know that as far as we're concerned, when we look at a molar mass, is what we call it, molar mass, we're looking at how many grams per mole something is. Okay? And when we look at atomic weight, we're looking at its AMU. But we can pretty much come to the conclusion that atomic weight is equal to molar mass. Based on what we saw here, the atomic weight, the AMU, is equal to the molar mass. Because our AMUs transferred over into a molar mass. And this is important. So in this situation, let's give ourselves an example here. Let's say we are combining hydrogen and oxygen to get water. And we have 50 grams of oxygen. We want to combine it with the proper mass of hydrogen to convert it completely to water. So how much do we need? How much do we need? So we need to figure out how many moles of oxygen are present. We have 50 grams of oxygen. We know that that's 1 mole of oxygen is equal to 16 grams of oxygen. So if we cancel grams of oxygen, we're going to be left with moles. So 50 divided by 16, let's break out our handy dandy calculator here. Where is it? 15 divided by 15. Oh, Lord. Clear. 50 divided by 16. We have 3.125. 3.125 mole. All right, so now we know how many moles we have of oxygen. Now we know that hydrogen, again, we're going to bring it up here, H2O. We have 2 hydrogen atoms per oxygen atom. So we need twice this many moles times 2. And that's going to be, what, 6.25 moles. So we need 6.25 moles of hydrogen. And we know that hydrogen, 1 mole of hydrogen, is equal to 1 gram of hydrogen. So we need exactly 6.25 grams of hydrogen. And that is the whole point of the amount section. It links us to where we can actually measure things in something that's quantifiable, and we can link between the amount of a substance, how many elementary particles we have of a substance, to the mass of the substance based on the information provided to us from the periodic table.